Mars, the red planet, has long captured the imagination of scientists, space enthusiasts, and science fiction writers. As Earth faces environmental challenges and resource limitations, Mars stands out as the most plausible candidate for human colonization in the solar system. However, transforming Mars into a second home for humanity is far from easy. While the allure of settling a new world is strong, the harsh realities of Mars present some formidable challenges. In this article, we'll explore the major technological, physiological, psychological, and environmental obstacles humanity must overcome to make Mars colonization a reality. Mars has emerged as the most feasible option for human colonization for several reasons. 1. Proximity. Mars is the closest planet that offers potential habitability. At its closest, Mars is around 55 million kilometers, 34 million miles from Earth. In comparison, Venus, though nearer, has an extremely hostile environment with surface temperatures of 900 degrees Fahrenheit, 475 degrees Celsius, and clouds of sulfuric acid. 2. Surface conditions. Mars has day-night cycles similar to Earth's, with a Martian day or so being roughly 24.6 hours long. While Mars' atmosphere is thin and mostly carbon dioxide, its surface gravity, about 38% of Earth's, makes it easier for humans to adapt compared to planets like Jupiter or Venus, where gravity would crush us. 3. Water. One of the key requirements for life is water, and Mars has it, albeit frozen in polar ice caps or locked beneath the surface. Recent missions have confirmed the presence of subsurface ice, making it a vital resource for colonists. 4. Geological history. Mars once had flowing rivers, lakes, and possibly oceans. It's conceivable that it might have harbored life in the past, making it an exciting prospect for scientific research. Despite these promising factors, the challenges are profound. Let's break them down into categories. 1. Technological challenges. Transport and entry into Mars' atmosphere. One of the first significant challenges is simply getting to Mars. Current spaceflight technology takes between 6 to 9 months to travel from Earth to Mars. This lengthy journey exposes astronauts to extended periods in microgravity and space radiation, both of which have serious health implications. More on that later. Moreover, landing on Mars is no easy feat. Mars' thin atmosphere offers little in the way of drag to slow down incoming spacecraft, making entry and descent particularly dangerous. NASA has famously called landing on Mars 7 minutes of terror. The recent success of rovers like Perseverance is encouraging, but sending and safely landing much larger human habitats, vehicles, and equipment is a major engineering challenge. SpaceX's Starship is currently the most advanced system aimed at Mars, designed to land large payloads, but it's still in the testing phase. Sustainable transport. Interplanetary travel to and from Mars will need to be sustainable, especially if a colony is established. Resupply missions from Earth would be expensive and take months to arrive. Therefore, self-sufficiency will be key to long-term survival. Spacecraft will need to be reusable, and we must develop technologies to efficiently transport resources and people back and forth. 2. Creating a livable environment on Mars. Mars' atmosphere. Mars' atmosphere is thin and composed mostly of carbon dioxide CO2, making it unbreathable for humans. There's no ozone layer to block harmful ultraviolet UV radiation, and the atmospheric pressure is less than 1% of Earth's, which means without protection, human blood would boil at Mars' surface. The first priority for colonists would be to live in sealed habitats with controlled environments. These habitats would need to be pressurized, contain breathable air, a mixture of oxygen and nitrogen, and shield residents from radiation. Terraforming Mars. A long-term goal of colonization may involve terraforming Mars, or modifying its environment to make it more Earth-like. Terraforming could involve processes like releasing greenhouse gases to warm the planet and thicken the atmosphere, or introducing plants and microbes that could convert CO2 into oxygen through photosynthesis. However, this is a monumental task that could take centuries, if not millennia, and would require technological breakthroughs that are currently speculative at best. 3. Resource utilization and sustainability. In situ resource utilization. ISRU, given the difficulty of transporting materials from Earth, settlers on Mars will need to use in situ resource utilization, ISRU, the process of creating necessary materials from what's already available on Mars. This includes water, extracting water from ice deposits or the soil. NASA's Mars Ice Mapper mission, planned for 2030, is expected to pinpoint water-rich areas for future colonies. Air, extracting oxygen from Mars' CO2-rich atmosphere. NASA's MOXIE experiment, Mars Oxygen In Situ Resource Utilization Experiment. Aboard the Perseverance rover has already successfully produced oxygen on a small scale by splitting CO2 molecules. Scaling this up would provide breathable air and fuel for rockets. Food. Colonists will need to grow their own food. Due to Mars' cold temperatures and lack of liquid water, traditional farming methods won't work. Advanced techniques like hydroponics, growing plants in water, or aeroponics, growing plants in an air/mist environment, will be essential. Plants will also play a critical role in recycling air and water within habitats. Energy. Colonies will need energy sources to power habitats, vehicles, and life support systems. Solar power is a possibility, but because Mars is farther from the Sun, solar energy is only about 40% as effective as it is on Earth. Nuclear energy, particularly small modular reactors, may be the most reliable source of power. 4. Physiological challenges. Gravity and health. Mars' gravity is only 38% of Earth's. While this is better than the zero-gravity environment of space, it could still have long-term health effects on the human body. Studies from astronauts on the International Space Station, ISS, have shown that microgravity leads to muscle atrophy, bone density loss, and cardiovascular problems. Over time, Martian colonists could suffer similar effects, even though Mars has some gravity. Moreover, a major concern is how children born and raised in Mars' lower gravity might develop. Their bones, muscles, and organs may grow differently, potentially making them unable to return to Earth's higher gravity without medical intervention. Radiation. Mars lacks a protective magnetic field and a thick atmosphere like Earth's, so the surface is bombarded by harmful cosmic rays and solar radiation. Prolonged exposure to this radiation increases the risk of cancer, genetic mutations, and organ damage. To mitigate this, Martian habitats will need to be heavily shielded, either by being built underground or using materials like water, regolith, Martian soil, or advanced radiation-blocking substances. Developing effective radiation protection is critical for ensuring long-term health on Mars. 5. Psychological challenges. Isolation and confinement. Living on Mars will be isolating, both physically and psychologically. Communication with Earth will have a delay of up to 22 minutes due to the vast distance. This time lag makes real-time conversations impossible and could make Mars colonists feel cut off from the rest of humanity. Additionally, settlers will likely live in small, confined spaces for long periods, which could lead to psychological stress, depression, and interpersonal conflict. NASA has been studying the effects of isolation through experiments like the HIC's Hawaii Space Exploration Analog and Simulation, where volunteers live in a Mars-like habitat for months. These studies suggest that mental health will be one of the biggest challenges for long-term colonization. Boredom and productivity. Keeping settlers mentally stimulated and productive will also be critical. Unlike Earth, where diverse environments, outdoor activities, and social connections are readily available, Mars will initially offer few distractions or entertainment. Colonists may face boredom and frustration as they adapt to the monotony of life on a barren planet. 6. Economic and political challenges. Cost of colonization. Colonizing Mars is not only a scientific and engineering challenge, but also a financial one. Space missions are extremely expensive, and building a permanent colony would require trillions of dollars in investment. Governments and private companies like SpaceX are working to lower the cost of space travel, But the sheer expense of sending people, materials, and infrastructure to Mars remains a significant barrier. Furthermore, who will pay for Mars colonization? Will it be funded by taxpayers or through a combination of government and private investment? The economic model for sustaining a Mars colony, whether through mining, scientific research, tourism, or other industries, remains speculative. Governance and ethics. If Mars is colonized, who will govern it? Current international space law, as outlined in the Outer Space Treaty of 1967, prohibits any country from claiming sovereignty over celestial bodies like Mars. However, as colonies grow and become more autonomous, new legal frameworks will need to be established to govern trade, property rights, and conflict resolution on the Red Planet. Colonizing Mars is a daunting but potentially achievable goal. While the challenges are immense, ranging from technological and physiological to psychological and political, human ingenuity has consistently overcome seemingly insurmountable obstacles throughout history. In the coming decades, advancements in rocket technology, life support systems, and resource utilization could make the dream of Mars colonization a reality. But it won't happen overnight. Mars colonization will likely proceed in stages, with initial missions focused on exploration and survival, followed by the gradual establishment